Thank you, Professor Nakata, for kind introduction. And also, I'd like to thank you, Professor Takashi Mori, for giving me a chance to give a talk today. So let's start. So first of all, so I want to remind you about the amazing ability of plants. So that is the plants collect a low concentration of CO2 from the atmosphere and to reduce this stable CO2 to synthesize glucose even at room temperature. And also water was used for oxidation reduction. And finally, it's perfect from the perspective of the LCA, life cycle assessment. So naturally propagate and no waste. So this is quite amazing. And also, plants fix a large amount of CO2. For example, this slide shows the goal of our laboratory. So the most biomass exists in forest ecosystem, and quite a large amount of carbon dioxide is assimilated annually. So this is 10% of atmospheric CO2. So that's why this system is very interesting for the CCS, carbon capture and storage. So biochar, wood is converted to biochar to store the land. So that reduces the carbon dioxide concentration of the atmosphere. So this amount, 10%, is correspond to the 4 to 5 times of the world energy demand. So that's why our laboratory intend to develop the technology of wood conversion technology into chemicals, fuels, and other very useful materials. So, this slide shows the biomass conversion technologies that involved 2 large groups. One is the thermochemicals, the other is biochemicals. So today is to focus on the thermochemicals. So conversion to produce heat, and the heat is also utilized for power generation. But the problem is the low efficiency. So pyrolysis have the potential to produce liquid fuels, charcoal, and chemicals. But the low product yield and low selectivity is a problem. And gasification also have the potential to provide the high efficiency electricity production by the gas engine turbine. And also petroleum chemicals can be produced. But the tar and coke problem is a great issue for commercialization. So for some chemical conversion technologies, the major challenge is how to control the reaction. So this is the very contrasted to the biochemical, as like the previous talk. So in this case, how to increase the reactivity. And also some chemical way also can contribute this increase in reactivity. So for this reason, so we have studying the molecular mechanism of wood burning, particularly the pyrolysis, because wood burning is a two-stage process. Firstly, the pyrolysis to produce the volatile charcoal, and these intermediates finally converted to produce heat. So when we started, we have studied these mechanisms for 20 years. But when we started, these molecular mechanisms tended to be treated as like the black box, so almost nothing known. So we intended to elucidate the molecular mechanism to control the reaction. So now, we have some information. So that is reviewed in some recent review. This is the review of reaction and molecular mechanism in cellulose pyrolysis in 2016. And this is the lignin pyrolysis reaction in 2017. So this is the major topics of this today's presentation, the fundamental characteristics. One is the pyrolysis products are unexpectedly unstable against heat. So I think most of the people do not know this very important characteristics. So today's talks mostly I focus on these topics. And lastly, is briefly introduce the influence of ultrastructure of cell wall. This is also quite important to control the reaction. Okay. So some chemical conversion is the two-stage process, as I explained the wood burning. So firstly, wood component is degraded to form the gas, liquid tar, and solid char. We call this process is primary pyrolysis. And then these products suffer from the secondary pyrolysis reaction to produce the final products. For example, charcoal, bio-oil, gas, and chemicals. So this intermediate primary pyrolysis products, reactivity to these intermediates are quite important for these some chemical conversion processes. So this is the example of the cellulose pyrolysis. So this is a thermogrammetric analysis of cellulose. So cellulose is heating, so around 350 weight suddenly decreased, and then the residue amount is stabilized. So primary pyrolysis occur in this temperature range, around 350. And then in this primary pyrolysis, large amount of levoglucosan, this is the anhydrous sugar, anhydrous glucose is produced. So please remember, this is the primary pyrolysis product from cellulose. This is a lignin thermogrammetric analysis of lignin. Lignin is similarly to produce large weight loss occur similarly around 350, but they are slightly the wider temperature region because of the heterogeneous structure. And in this temperature range, coniferal alcohol, this is produced. So this is the actually the biosynthesis, the monomers utilized for biosynthesis of lignin. So that means the back reaction takes place at high temperature. But the coniferal alcohol is not usually recovered as the pyrolysis product of lignin because of the secondary reactivity is quite high. Okay, and for lignin, unlike the cellulose, at high temperature, still weight is decreased. That means the lignin-derived char is unstable compared to the cellulose. So metal could become reactive with this temperature, and benzene ring is clipped to form the coke and gas. And many reactions takes place, but these reactions are not focused today. So these primary products, levoglucosan and coniferal alcohol, these are quite unstable against heat. This is a quite important, gave the quite important suggestion for us. For example, these products may be degraded in recovering system. So because of we need to cool down to these gaseous products, and also coking and tar and coking problem related to this characteristics. So from the next slide, I will explain some example of the how unstable and how to improve the stability. Okay. So this is the cellulose-derived volatile products in fate of the cellulose-derived volatile products in gasification. So so here at the bottom, cellulose is placed, and this reactor is placed in the furnace, this temperature profile. The bottom cellulose is heated at 800, and around here is the less than 100. So that means the cellulose is pyrolyzed to produce the volatile product, and in the gas phase, gasification reaction takes place, and unreacted intermediate condense into the liquid phase around here. But the interesting point, what is interesting is after tower extraction, these materials cannot be completely extracted, removed. These are the coking, carbonized materials produced. That means, that's why I like that. So cellulose-derived volatile products become reactive by cooling. But actually, this is not merely by merely cooling. By cooling, the phases change from gas to liquid. This is the big difference. Okay. And to check the which intermediate products cause the coking by cooling. So we studied these components. Each component is put on at the bottom of the ample reactor, and that amount is the enough amount that can be completely volatile in the ample. That means no residue. If the completely volatile, no residue. And in the ample and nitrogen, so ample is heated. So the sample is suffer from the molten phase reaction, and this reaction competes with the evaporation. So with this, and then in the gas phase reaction takes place. If the coking reaction takes place, even in the gas phase, glass is covered by the coke. And particularly, we focus on this side because if the coke is produced here, so this coking reaction takes place below the boiling point, that's a dew point. So this is the results. So the Frank type compound produced the gas phase coking, but here, so almost no gas phase coking. That means the that is explained by the small, almost very small amount of the yield for production of these. But so these components produced the liquid phase coating. And here, so the boiling point is plotted here. So levoglucosan and 5-HMF is very much to the coating place. That means but the 5-HMF, the production yield is quite low. That means the levoglucosan caused the coating. So these results indicate the levoglucosan initially produced and in the gas phase, gasified, but after condensation to the liquid phase, suddenly become reactive to convert char, okay, coke. So this very improved reactivity in liquid phase is clarified due to the hydrogen bonding that act as acid and base catalyst. For example, here, so this red one acts as the hydrogen bond donor, acts as acid, and the hydrogen acceptor acts as base. These catalytic activity is effective only in the gas phase. Okay. And also, these results suggest the secondary reaction of these components occur in non-radical mechanism. And to stabilize these components in the liquid phase, we found it's very simple, just blocking the hydrogen bond, like in the gas phase. And also in hydrogen bond acceptor solvent, like the polar ether and aromatic substance. For example, aromatic substance OH-pi interaction is formed. That means this suppresses the intermolecular hydrogen bonding of levoglucosan. And also polar ether, the oxygen, acts as the hydrogen bond acceptor. So this is the example of the polar ether. We use this polar ether and heated 30 minutes. So this is levoglucosan under nitrogen in this temperature range. So levoglucosan is completely carbonized. But in this polar ether, almost completely recovered and almost no color. But glucose is relatively much more reactive because of this is reducing sugar and a little bit delayed in this polar ether. But the product composition is quite different. So as you know, so glucose is converted to caramelized products like the the heating on pan. But in polyether, this reaction completely inhibited, and at a slightly higher temperature, selectively fragmented into these C2, C3, and C1 compound, and yield is up to 75%. So we can easily control the reaction by changing the hydrogen bonding pattern. And this is the in aromatic solvent. In aromatic solvent, levoglucosan is stabilized up to 340 completely in this aromatic solvent. And this activity is correlated with the pi electron density. So if this is possible, so we can get the levoglucosan. This is also useful for the fermentation because of the hydrolysis of levoglucosan quite easy. So, but the still application to cellulose and wood is quite challenging because of the due to the effect of the crystalline structure. So later I will briefly speak. So for coniferous alcohol, so we add the bottom of glassware, and this is heated, and then after the pyrolysis, glassware is cut off, and each glassware is extracted. So based on these results, we can easily identify how much evaporate, how much remain. Okay, and this is the results 200 to 350. The coniferous alcohol recovered from the bottom is so significantly decreased. And at 300 degrees Celsius, almost nothing. And evaporated coniferous alcohol that is recovered from the upper side is also quite small. So this coniferous alcohol is stabilized at the upper side, where the reaction temperature is lower. But the major component product is condensation product, that's a polymerized product. And also side chain conversion product is produced. And please remember the primary pyrolysis reaction takes place in this temperature range. So if the coniferous alcohol is produced, mostly the product is condensation product. And also coniferous alcohol side chain structure change from trans to cis, and oxidation, reduction, and side chain break. And interestingly, lignin pyrolysis products, so that monomer, lignin-derived monomer is quite similar, and the composition also very similar. That means these products may be from the secondary degradation of the coniferous alcohol. So this is the condensation mechanism and its control. So in lignin pyrolysis, ether cleavage is quite easily occur, but mostly in the radical mechanism. That means the initial product is radical. So radical is easy to coupling to condensed products. This is one mechanism. If a radical abstract hydrogen to stabilize the coniferous alcohol, but this is very easy to be to form the quinomethyl intermediate to form condensation. So actually, so we need to suppress these two condensation mechanisms. So for here, the H donor addition is effective, and here it's aromatic solvent because this is in this here proton transfer is necessary, like the levoglucosan stabilization. Aromatic solvent is quite effective. So last 1 minute. So briefly talk about the influence of ultrastructure cell wall. So mostly, most people do not focus on this, but actually this is quite important. So cellulose is the crystalline material, and the cellulose microfibril size is the 10 nanometer scale. But the cell wall is the several micron. That means the cellulose nanocrystal, aligned several hundred and thousand And also matrix hemicellulose and lignin cover around the cellulose microfibril. And microfibril is cellulose microfibril is quite stable because of the cellulose crystalline nature. And pyrolysis start from the surface. And but the if the cellulose, the no matrix, but the, for example, aromatic solute cannot penetrate into the surface. That's a problem. And for wood pyrolysis, so actually the hemicellulose cellulose reactivity is quite different from the isolate sample. That means the hemicellulose and lignin are very systematically arranged in the matrix, and that's changed the thermal reactivity. And also, we think we consider the lignin pyrolysis to prolong the radical. This may influence the hemicellulose. This occurs in the very narrow area of the matrix. This is a problem. So these kind of knowledge may be very important for the new ideas for the clean gasification, autosaccharification, bioprocess chemical production. Okay, thank you for listening.